Proteus. So Proteus is this JIT compilation and runtime optimization solution that we're doing for C++ using LLVM. I want to mention like all the members of our team that make this possible. So it's David Beckinsale, Konstantinos Parasiris, John Bowen, Tal Ben-Nun, and Thomas Titt. Some of them are going to be online with us now. So they're going to be here in Q&A for things that you might want to ask. So, diving right in, like what motivated us to do this work? So we work at an HPC lab. We want to get, maximum performance from our codes. It's high performance computing. And what we do with our software, it has its limitations. So the typical process when you develop HPC code is that you write your program in a statically compiled language like C, C++, or Fortran. That are fast. Then you compile it through a compiler, doing what we call, ahead of time compilation optimization, which means the compiler is going to take your program, it's going to compile them, it's going to compile it through an optimization pipeline, and at the end you're going to get an executable. And then you can do, very aggressive optimization. You can do, typically O3 when you compile to get the maximum performance that you can get from your code. But this has limitations because the compiler can only analyze and optimize the code based on whatever assumptions and information it knows at compile time, ahead of time, as we say, of that program. So ahead of time means ahead of execution time, so at compilation time. And we want to overcome some of these limitations, and we want to make specializations of our codes to make them faster. We want to give more information to the compiler and extract, every bit of performance that we could extract. So we do what I saw on this code on the right. So we write those compile time value specializations using templates. And basically, this means that we take, for example, a function, we template it, and then we start putting template parameters that are going to be runtime constants. So, for example, here we have this Q kernel, and then we have different specialization of that Q kernel that are encapsulating some of the values that we know are going to appear at runtime and that we want to optimize for. So apparently, this is not ideal. I mean, the code is ugly. We cannot enumerate all possible combinations of runtime values that can appear during the execution of the program. So we kind of compromise for a subset. And we also have to put this dispatch code that, we have our specializations. We need to store them somewhere, say in a map that are going to be relatively fast retrieved. And then we have to dispatch for them. So to kind of make all these things better, we started the Proteus project. It's a very young project. We started last October, and it's slated to last until 2027, so 3 years from now. We have a repo where Proteus is being developed, and like the project goal in one sentence is that we want to research and develop programmable JIT compilation optimization to maximize the performance of our HPC codes. Our great focus is on GPU compilation. Basically, the workhorse of HPC has been the GPUs for quite some years now. We get our performance and performance efficiency through GPU execution. So it's a feature that we definitely want to support when we do this JIT compilation optimization and performance optimization. So looking at the just-in-time compilation landscape, we know that it's very successful for interpreted languages like Java and Python. It helps a lot. JIT compilation optimization helps a lot by removing the interpretation overhead, because you can introspect the language, you can generate some intermediate representation, then you JIT compile it and execute it natively. Besides solving this interpretation overhead in those managed languages, JIT compilation optimization also does extra things like the value specialization that we have seen, and this gets extra performance. So this has been very successful. Now, if you move that to see how JIT compilation works on static languages like C, C++, and Fortran, there are challenges. So one is that introspection is hard. For those languages, typically things have been lowered to machine code. You don't see a lot at runtime. The compilation optimization that happens statically ahead of time has been something that has been developed and researched for decades. So it's really, really well done. So it's very hard to beat with those dynamic optimization techniques. And at the end of the day, there is overhead from JIT compilation. You have to make sure that your overhead is less than the performance that you can extract, if you can extract any performance trying to beat static compilation with just-in-time optimization techniques. So starting with those challenges, there is some prior work that showed limited success. So it has been inspirational, but it has like various problems. There has been EasyJIT, again targeting C++, and basically using an interface of C++ functors that you could specialize using placeholders. That work was about 8 years ago and based on Clang 6. And they didn't support GPUs, so it wasn't very useful for us to start from there, and it's been obsolete. So we are like at Clang 19 going to 20, and it's very hard to port such an old code. Now there's been another recent work which also our lab was involved, and it was called ClangJIT. So the idea again is that you can annotate part of your codes for JIT compilation, mostly focusing on C++ templates because they wanted to lower the compilation time of specializing a great number of possible template specializations at compile time. But as a corollary to that, they could also do value specialization, which is an important optimization that we do manually in our codes. So this is relatively slow, though, as a system to work with, because it has to start with C++ AST, and then it has to lower that AST to LLVM IR, perform semantic analysis and code gen, and then you have to take this LLVM IR and then analyze and compile it again. Another drawback was that this was coded in Clang 11, and again, it creates this obsoleteness problem for us. Now, there are also the non-portable CUDA and heap specific runtime compilation interface that NVIDIA and AMD are giving. There is also NVIDIA's GTFi, which is a kind of, an easier to use wrapper on top of the CUDA RTC that also provides value specialization opportunities. And those are good. They tend to be slow because you provide to them your source code to compile in a textual form, so in a C++ string or C string. And then the interface takes this code, it needs to parse it, load it to some kind of internal representation, and compile it again. But the biggest issue with using things like that is that it's not portable. And here at the lab and in general in HPC, we have this zoo of machines, so different machines, different GPUs, different architectures. So we like things to be portable. So moving on to that, we propose Proteus and trying to overcome those problems. And here I present, like, it's a very busy plot. I just saw the complete Proteus workflow, and then we're gonna start taking things apart and talking about them separately. But looking at the complete picture, we started compilation. So we asked from the developer to annotate their code for JIT compilation. And the interface that we have right now is attributes. So we have this generic annotation attribute called JIT that you can put in a function. And that indicates to Proteus that this function is going to be JIT compiled and optimized. And in that annotation, we also ask the developer to give us optimization hints that we're going to use at runtime. And the optimization hints that we use so far is asking the programmer to tell us which arguments of that function we can treat as runtime constants. So the programmer needs to give us the index of the argument. It's one indexed in our API. It needs to give us the index of that argument, and then we're going to make sure that we can extract the value of that argument at runtime, and we're going to use it as a constant value when we generate code. So going through that process, the developer is going to compile that program, the annotated program, with Clang LLVM, and Proteus is going to provide the plugin pass, and that plugin pass it's gonna operate on those annotations and do changes in the LLVM IR and the resulting executable. And the changes have to do with extracting LLVM IR, which is gonna be our common currency for specializing and optimizing LLVM code at the runtime. And it's also going to put like instrumentation routines and entry point routines. So when we call a kernel, we're going to go inside the Proteus runtime library and execute a kernel through that infrastructure. So assuming we have this in place, when the user executes the program, which has been Proteus compiled, the program is going to use the linked Proteus library when it executes a kernel. And when it executes a kernel, it's going to look, first of all, is this cached? So Proteus does caching of compiled code to remove overhead. If it's cached, it's going to go through a fast path. It's going to retrieve the code. It's going to get the binary, and it's going to execute it. Now, if it's not cached, that's when it's going to go through the compilation and specialization pipeline of Proteus. And this pipeline has 4 steps. In brief, we extract the IR, we specialize it using the runtime values of kernel arguments and other things, as I'm going to show. Then we do a step where we call global relinking. So we want to make sure that the device global variables that have been loaded by ahead of time compilation modules point to the same addresses as device global variables that we're going to use in our JIT modules. I'm going to expand on that later. And once we go through that step, we do a classical O3 optimization pipeline, or whatever the user chooses for the optimization pipeline, to generate a device binary, which we're going to execute on the hardware. So moving on to talk about those parts in more detail. So as I said, Proteus is basically implemented as an LLVM pass plugin that you can use with your Clang LLVM installation and the runtime library based on LLVM. So integrating those things is not too hard usually, in your build system for your software. So the LLVM plugin pass, you need to use an option when you use the Clang driver to say that I want to use this pass when I do this compilation. The runtime library, it's something that needs to be linked with your compilation, along with any LLVM libraries that we depend on. And to make this process easier and not having to do those changes manually, we also provide CMake exports. So we provide the CMake configuration and that you can use an add Proteus function, provide your target, and then those things are going to be taken care of. Now, starting from the plugin pass. So the plugin pass is set to operate when you do a compilation for CUDA and HIP on your code. And as a primer on how Clang works with that compilation is that it creates 2 compilation paths. It's called split compilation, and one compilation path is going to create the device LLVM IR, and at the end of the pipeline, the device object. And the other compilation path, it's going to create the host LLVM IR, and at the end of the path, the host executable. And what happens is that the device binary that gets generated by one path is going to be embedded in the host executable, and at runtime, the implementation is going to make sure that it can load the device binary and can execute kernels from it. So Proteus pass operates on both those branches of split compilation, and when we do the host branch, Proteus pass operates as a module pass. Module pass means that it's going to apply to the whole of the translation unit. And it does basically 2 things. One, it parses the annotations to figure out things about the kernels that are going to execute. So, the kernel symbol, runtime arguments, the places of those arguments, and so on. And it also instruments the host LLVMIR for the program. And the instrumentation follows closely what the HIP and CUDA runtimes do in terms of what kind of registration of information they need to bootstrap their execution. So we have a register FAT binary, register function, register var, and register linked binary routines that are going to call into Proteus. And I'm going to give a little bit more detail what those do later on. And the other thing that our instrumentation does is that it replaces launch kernels that were set to go into the CUDA or HIP runtime to execute through Proteus. Basically, we have this JIT launch kernel entry point that is going to replace, the typical CUDA or HIP launch kernel calls and make things work through Proteus. Now, when we do the device path of the compilation, the Proteus plugin can either be a module pass or an LLTO pass. The LTO pass is used for heap RDC compilation, but the functionalities between those two things are similar. And the only thing that it does when there is device compilation is it takes the bit code of the translation unit to compile or of the LTO program to compile, and it embeds it into the object. And it embeds this bit code, this LLVM IR bit code, by creating a global variable with a unique ID that's going to exist, and at the same time putting that global variable in a specially named section. And I'll talk next how we use that when to extract device bit code. So after the pass is done, it communicates with the Proteus runtime library by redirecting information, at the library, and also making sure that launching kernels happens through the libproteus library. And giving a little bit more detail on the registration functions, people that are familiar with the internals of CUDA and heap, they're going to find that there is like one-to-one correspondence to CUDA and heap runtimes. Register fat binary, it basically tells Proteus what is the unique ID of this device code binary, and it also provides the device binary code. And we're going to use it to actually extract the device bit code, the LLVM bit code. Register function tells to the libproteus runtime what is the kernel symbol that we're going to JIT compile and optimize, what are the indices of the constant arguments of that kernel, what are the types of those constant arguments, and how many they are. And register var, it's gonna give Proteus the information on what device global variables exist, and also where they are addressed. And register linked binary, it's used for CUDA RDC compilation, and it gives a unique ID to Proteus that Proteus can use either to extract device bit code if that linked binary, which is basically a device library, if it has been compiled with Proteus, or to just link with it as a binary when it creates a JIT module to code them. So those registrations happen once in the program. They mirror what happens with CUDA and heap runtime registration. And then the other instrumentation that we do is that we change the launch kernel calls to go through JIT launch kernel, and that replicates, the arguments of a typical CUDA or heap launch kernel, the kernel symbol, the arguments, the stream, the SMEM size. We replicate those things, but they go through Proteus in our case, so that we can do JIT compilation and optimization. Going to the runtime side now, the first thing that the runtime needs to do is to extract the embedded device bit code from the device binary that has been communicated through registration. So to do that, libproteus does different things depending on what the original compilation has been, whether it has been through CUDA or heap. So through CUDA, we basically do a mem copy for the global variable that's going to store this code, uniquely named using the unique ID, and we're going to mem copy from the device to the host the bit code and start to operate on that. For the AMD case, we basically look at the section that is uniquely named, and we extract the LLVM code from that section in the binary. We cannot use the same section idea and approach with NVIDIA, because the NVIDIA proprietary toolchain, when you create a device binary, it throws away all sections that are non-standard. So at the end of this extraction, the Proteus runtime library is going to have the LLVM IR of the device bit code to start doing things on it. And the next thing that we want to do with that bit code is that we want to generate a JIT module. So we want to generate the LLVM IR of our module to execute. And we want to specialize it. We want to leverage as much runtime information as there is to specialize this JIT module to help the compiler optimize down the line. We have three specializations that we do so far, and we are developing to create more. One is the kernel argument specialization that I talked before. So what we do, like with value specialization in C++ templates. So we fold to runtime constants any kernel arguments that have been designated by the programmer. The other specialization is on launch bounds. So we can set launch bounds dynamically on a kernel to optimize the pipeline data role and especially register allocation when we code-gen binary. And the last specialization that we do is to fall to runtime constants, also launch dimensions that we know at JIT time what they're going to be when we execute the kernel. So we can basically remove reading the dimensions when you do code in the kernel, and we can also inject like LLVM assume intrinsics, and those intrinsics can put bounds on the values of those possible launch dimensions and help the compiler optimize. So I have an example here using again this DAXP kernel. The example is in C code, but those transformations and modifications, they actually happen at LLVM IR. So C code is just easier to see things. So let's say, we start with this kernel here. We have our AX plus Y kernel with double precision. So the DAXP kernel here, and it's a nice threaded loop that we execute on the device. And there is this annotation. I think I can do laser pointer here. Yeah, okay. And we have this annotation from the programmer here, to JIT it, and we say, I want you to fall to constants the first argument, which is the scaling factor here, double A, and the second argument, which is the length of the arrays to do the DAX calculation. So what libproteus is going to do, assuming the LLVM representation of that code, is create this equivalent implementation. So it's going to put a specific launch pouch that we're going to know at runtime, because we know with how many threads we are going to be executing with. It's going to replace the dimensions and the block dimensions and grid dimensions with the number of threads and number of blocks as constants. And it's also going to change the loop. And instead of iterating over variables for some of the things, we're going to have like constants and specialize that to the specific values of N and A that the kernel has been launched for. So after we do this specialization, we do what we call relinking the device globals on that LLVM IR. Again, I'm going to show how things are happening on the source code, but it's the same transformation, but it happens at the LLVM IR, which is what libproteus has access to. And explaining a little bit what we do and why we need to do it. So device global variables, let's say we have this code on the left. Device global variables, they're going to reside in the GPU device memory, and all the kernels are going to be addressing the same device memory when they access device global variable, and they will accessing the same global state. So this works fine and well for ahead of time compilation, but for JIT compilation, things are a little bit more complicated. So ahead of time compilation, we have a program like this, where we have two kernels. Those two kernels access this global variable. That's fine and well. At runtime, they're both going to access this global variable, and I'm not going to look into whether there is a race or not. They're going to access this global variable, so that works fine and well. Now, when we create a JIT module, the JIT module, if we just create a device global variable in that module, this means that at JIT compilation, we're going to be creating a new global variable at a different device memory address that things are going to be operating on. And apparently, we don't want that. We want our kernels from ahead of time compilation and the kernels that we JIT to always access the same device memory in that global variable. So what we do is that when we create a JIT module, we create an indirection for accessing this variable. And this indirection is basically a pointer whose value is going to be the address of the ahead of time loaded global variable, and it's to be set later. I'm going to show how we do that. We use the CUDA or heap get symbol address API to get the address of that global variable at runtime, and then patch it there. And when we do that, we are going to have access to the same device memory through the global variable in both the JIT and ahead of time modes. So going away with this complication, we are at the last step of libproteus JIT compilation optimization, and we have our relinked LLVM IR. We passed through an aggressive optimization pipeline, so all the specializations that we applied before, we expect that they're going to help all three create better code and faster code. So we get this optimized LLVM IR, and then we can do code gen, get the device binary that's going to be executing on the machine, and that's where we do our patching for the global variable address. So basically, we look at the object file, we found the initializer of that global variable pointer, and we put the address of the global variable that we want to use. So after this patching, we have our final binary, and that final binary we can launch and execute on our GPUs. So that's the slow path. That's the path that we haven't cast this before, so we have to do all the process of JIT compilation optimization and all those steps here. Now, if we look at the fast path, so the fast path goes through caching. So you go through libproteus, you say, have I cast this compilation result before? If that's a yes, then you can go into caching, you can get it and run it. And caching in Proteus has two levels. We have the in-memory cache, and we have the persistent storage cache. And the persistent storage cache is in the file system. The in-memory cache apparently it's created in memory while the program runs. The persistent cache it's stored and it persists across runs of the programs, and it's basically used to feed the in-memory cache. Now, the compilation result that we cache is the kernel along with all its specializations. So every specialization of the kernel, it's basically a unique entry in that cache. And the way we do it is that we create a unique hash that comprises of the hash of the module, so of the module code itself, the hash of the kernel symbol, and the hash of its runtime data, be it kernel args, launch bounds, or launch dimensions. Those things get hashed together and they create this unique hash for this specialization of the code. And then all those specializations are going to be stored individually and retrieved individually from the cache. One particular complication with JIT code is that one would like to invalidate or at least not use JIT code for something if they change the source code that created it. And that's a little bit tricky because you have to make sure that you can understand changes like that. But we have this hash module here exactly to make this caching responsive to source code changes. So we believe this works well, and it definitely doesn't allow you to get like stale entries from the cache. But we're still working on how to make the cache more efficient, make sure that we have like good and efficient eviction strategies and all those things. So this is, I mean, it's working, but we're definitely expanding on it. So concluding a little bit with what Proteus does, we support right now both NVIDIA and AMD CUDA and HIP codes. We support RTC or non-RTC compilation, and we also support device libraries, whether they have been compiled with Proteus or without Proteus. We try to develop things for robustness and generality as well. We are going to be using, and we are using Proteus in one of our large mission applications that the lab is deploying, and we already have like successful deployments with Proteus in those. We do continuous integration testing. We test also on GitHub and our internal GitLab CI, where we have access to our GPU machines. We test for LLVM 17 and 18, CUDA 12.2, and two flavors of ROCm, 5.7.1 and 6.2.1. And it's pretty actively developed. I mean, we're a small team of 5 developers, but we're definitely on top of it. Now, we want to, okay, we have these ideas, we have an implementation, we want to benchmark it and see what kind of performance do we get. How well does it work? What are the overheads? Is that reasonable? How do we go on about this? What do we need to focus our development? What do we need to improve? So to do that, we take a heterogeneous computing benchmark suite, which is called HECBench. And it's a suite that comprises of HPC proxies and kernels, and not only limited to HPC, it also has like kernels from other domains as well. It's pretty well maintained. It's curated by Oak Ridge National Lab and Intel. And they have lots and lots of implementations there of kernels in different programming languages like CUDA, HIP, SQL, OpenMP offload, so quite a variety. So we take programs from different domains out of that benchmark suite, and we test them on two of our platforms. One is using NVIDIA V100 GPU, the other AMD MI250X. And we have several comparators in terms of performance. One is what is ahead of time compilation doing, AOT. The other one is what is Proteus doing, assuming we don't have, we haven't cached things before. It's the first run of the program. We don't have a persistent cache to pull things from. The other flavor is Proteus plus caching, so things have been cached. And then when you execute the Proteus, you don't have to do the runtime compilation. You have things ready-made from before. And then we also compare with GTFi, which is NVIDIA's interface, again, only for CUDA codes, that does similar things with just-in-time compilation and optimization, resulting in the interface of, as I said, C strings of the code that are going to be compiled and optimized through that interface and CUDA RTC at runtime. And this is the 6 benchmarks that I'm going to show here: Adam, RSPENS, WSM5, Feynman CAC, Lulesh, and SW4CK. So those are all pretty interesting programs for HPC. NML. So the first observation that we want to do is what happens if we take a program, if we execute it only after it has been ahead of time compiled and optimized. What is the end-to-end execution time? Like from start to finish, what performance do we get? And then we do the same thing with Proteus. So not including a cache exposes the full runtime compilation overhead. Then Proteus plus cache, which means that things have been pre-cached, so no runtime compilation overhead, just get the specialized and optimized kernels and execute them. And that last one is GTFi. So we have results here on the NVIDIA machine and results here on the AMD machine. The interesting result is that Proteus makes programs go faster despite its overhead, and sometimes it has like significant improvement in end-to-end execution time. And this improvement is even more pronounced when we start from a cache. So we don't have the runtime compilation overhead, but we reap all the benefits of having pre-optimized the kernels that we're going to execute. The other observation is that we see that GTFi is a little bit struggling to get end-to-end performance from some of their codes. Only one, WSM5, which is a weather simulation code, is one that GTFi does really well. And on the rest, it seems to have like slowdown, like below 1. Speed up over ahead of time compilation below 1 means we're getting slowed down. Now things on AMD, they look again very favorable for Proteus. Again, we do speed up over ahead of time compilation, looking at end-to-end execution time, and in all the cases, Proteus is able to optimize better. So okay, this experiment showed us that okay, things are going well. And then we wanted to make another experiment and say, okay, we want to see what kind of overhead do we bring by having the execution go through Proteus. And we made an experiment where we compile and use Proteus, but at runtime we don't apply any of the specializations. We just use the O3 pipeline with whatever code has been coming in from ahead of time compilation. And that is going to show us a little bit, how much, what is the overhead of Proteus compared to an equivalent optimization that happens ahead of time, and whether this is manageable or not. Again, results are pretty good, both for the NVIDIA V100 and the MI250X machine. Proteus doesn't introduce typically more than 10% overhead. So this is definitely manageable. And as we saw in the end-to-end execution time, we can recover it and get speed up at the end. So we decided to look a little bit more closely on the GTFi result, and we were trying to understand why GTFi is slower end-to-end to Proteus. Like what is the problem? Is it that it's the overhead that we suspected starting from textual source code, or is the code generation that GTFi does that creates kernels that are not fast? So it turns out that it's mostly the overhead, and the experiment to do that is we look again at the speed up over ahead of time compilation, but we only look at kernel execution time. So we want to see how good is the device code that Proteus generates and how good is the device code that GTFi generates. And what we see is that Proteus has pretty good code generation. It has like better code in 3 of the 5 benchmarks that I saw here. I don't show Lulesh because GTFi errors out if you try to compile Lulesh. So 3 out of 5, Proteus has like better code. GTFi does really well and creates much more optimized code for WSM5, which also explains why the end-to-end execution time with WSM5 and GTFi was actually giving speed up. But it struggles otherwise. So at the end, it's both a combination of the overhead from the GTFi path of compilation and in some cases not getting as fast code as possible despite the same specialization that we try to do with Proteus. So the last plot that I have to show, and it's probably the busiest one, but it's an ablation study that we do. Again, we do speed up over ahead of time, but looking only at kernel time, and it's an ablation study that we do where we take Proteus and we apply only one of the things that Proteus tries to specialize for. So we apply only the dimension constant folding, or the launch bounds constant folding, or the runtime argument constant folding, and see what kind of impact does it have in the end performance of the kernels of different programs. The results are mixed. We always get speed up, or at least most of the times we get speed up. And sometimes it's the runtime constant folding. Sometimes it's the launch bounds that helps a lot the register allocation later on in the pipeline. And sometimes we get like small improvements by dimensions and launch bounds, and then those things tend to accumulate and create a bigger speed up. But it's an interesting result, and it shows that different specializations that Proteus does, at the end, they work together and you get speed up from one or the other of the combination. So I hope I didn't tire you a lot. So as a conclusion, we have the Proteus project. We implement JIT compilation optimization targeting C++ codes using LLVM. We have this attribute-based annotation interface for JIT compilation optimization. We have shown that we can get pretty good speed up from this specialization on AMD and NVIDIA. We're actively developed and have a GitHub repo. We are very happy to engage with people. And as future work, we're going to look at a scaling of Proteus, so distributed JIT compilation on multitude of machines, look out for more optimizations and develop more optimizations, make sure that we have more efficient code caching, and make sure that Proteus overhead is so small and its optimization is so good that we can deploy it in a lot of our programs and get significant performance. That's it. Thank you. Happy to take questions, and feel free to email me as well.